In every space movie ever made, the exposed body freezes. The visor cracks, ice crystals form on skin. The vacuum rushes in like a cold that has been waiting outside the door. You have seen this scene so many times it stopped feeling like fiction and started feeling like physics. It didn't. Space doesn't freeze you. It traps your heat and slowly cooks you from the inside. The temperature gauge inside the suit is climbing, not drifting, climbing. The astronaut is motionless. No exertion, no sunlight hitting the suit directly. The station's shadow covers everything, and the number keeps rising. The cooling system is running at full load, not to add warmth, but to fight heat that has nowhere to go. Sweat is building inside the helmet. The air near the skin is warmer than it should be. Everything the movie said would be cold is generating heat in a sealed container with no exit. That is not a malfunction. That is the physics working exactly as designed, exposing the design's limit. Temperature is not a property of empty space. It is a property of particles. Temperature measures how fast molecules are moving. In a vacuum, there are almost no molecules. There is nothing to be hot or cold in the sense a room is hot or cold. The vacuum is not waiting to pull warmth out of your body the way winter air does. It is not cold the way a freezer is cold. It is empty, and empty means no medium, and no medium means heat has almost no way out. On Earth, your body sheds heat in 3 ways. Touching a cold surface transfers heat directly through contact. Air moving across your skin carries heat away constantly, even when you are still. And your body emits infrared energy outward, which is real heat loss, but slow. The first 2 mechanisms are fast. They are the reason a cool room feels comfortable and a hot room feels unbearable. Take away the medium, the air, the surfaces, the fluid contact, and only the third one remains. In vacuum, thermal radiation is the only exit. Radiation moves heat, but not quickly. The same warmth that a light breeze removes from your skin in seconds takes many minutes to radiate away into empty space. The math is not close. Convection in moving air removes heat roughly 1,000 times faster than radiation into vacuum. Your body at rest produces about 80 watts of heat, the equivalent of a household light bulb, running continuously inside your skin. During a spacewalk, working with tools, moving equipment, the output rises toward 500 watts. 5 light bulbs inside a sealed suit with no air. In a vacuum that does not pull a single degree away from the outside of the fabric, that heat has to go somewhere. The only exit is the cooling system built into the suit. It runs water through a network of tubes pressed against the astronaut's skin. The water absorbs the heat the body generates. It carries that heat to a device at the back of the suit called a sublimator. The sublimator releases the heat by slowly evaporating water into the vacuum in a controlled stream. The evaporation carries the thermal energy away with it. No evaporation, no heat removal. The suit is not a heating device. It is a heat disposal device. The cold it creates inside is engineered. The warmth it fights is biological. If the system stops, the astronaut does not drift toward ambient temperature. There is no ambient temperature. The astronaut's body keeps producing heat into a sealed, insulating shell. Core temperature rises. The timeline is not forgiving. 20 minutes after cooling failure, core temperature approaches the threshold where heat exhaustion begins. Thinking slows, hands become less precise. The tools needed to address the malfunction become harder to use at exactly the moment they are needed most. At around 30 minutes, without rescue or restoration, core temperature crosses into heat stroke. Consciousness begins to fail. Communication degrades. Self-rescue is no longer physically available as an option, not because the astronaut chose wrong, but because the biology has gone past the threshold where choice is possible. At the same time, the heat building inside the suit is not staying in the biological environment alone. The electronics in the suit are also warming. Thermal expansion begins in materials that were calibrated for a specific operating range. Seals that fit precisely at normal temperature begin to shift. Circuit responses slow or stop. The systems designed to signal distress or guide a rescue are failing in the same thermal event that is disabling the person they are supposed to protect. The suit becomes a compounding environment where each failure narrows the remaining options for the next one. The point where the failures converge is specific. It is not a gradual deterioration. It is a threshold moment. July 2013. Italian astronaut Luca Parmitano was outside the International Space Station on a routine spacewalk when his helmet began filling with liquid. Not ice, not frozen gas. Warm water, the coolant from the suit's own thermal management circuit, leaking from a failed separator inside the system. Within minutes, the water covered his eyes. It reached his nose and mouth. The mission was terminated under emergency protocols, the most dangerous, unplanned spacewalk conclusion in ISS history to that point. Parmitano navigated back to the airlock, unable to see, guided partially by memory of the station's layout, as the warm water continued accumulating inside the closed environment of his helmet. The incident report identified the cause as a clogged water separator, allowing liquid to escape the cooling loop. The fluid threatening his life was not cold. It was the heated output of the system built to keep him alive. The warmth was the emergency. No movie scene had prepared anyone to expect that. The film version of Spacesuit failure always involves cold fluid, cracking seals from ice, crystallized equipment, frozen breath. The Parmitano incident was the opposite in every physical detail. The medium was warm. The origin was the thermal management circuit. The timeline was minutes, not seconds, and it escalated not through cold, but through the slow accumulation of warm liquid in an enclosed space with no drain. The documentation of the event produced detailed engineering reviews of water separator design across the suit fleet. The thermal management system received the same level of structural scrutiny previously reserved for pressure seals. Cold was never the item on the risk register. The smart solution the viewer reaches for at this point is geometry. If the suit is overheating, point it toward the dark side of the orbit. Let it face the coldest possible background, deep space, far from the sun, facing away from the station's heat output. Radiate the excess heat directly into a 3-degree background. Space is cold, after all, in the sense that the cosmic background temperature is nearly at absolute zero. If the vacuum radiates heat away eventually, then face the coldest possible direction and let physics take its course. The arithmetic disagrees. Thermal radiation depends on surface area and temperature difference. The suit radiates infrared energy outward continuously, but the rate at which it can export heat this way is set by the suit's surface temperature relative to the background. The gap between roughly human body surface temperature and the cosmic background is large in absolute terms, but the rate of radiation that gap produces is still far slower than 80 watts of metabolic output at rest and nowhere near 500 watts during exertion. The suit would need to be substantially hotter than human tissue, hotter than survival allows, to radiate fast enough to match metabolic production. The geometry of pointing toward shadow does not change the fundamental rate at which infrared energy leaves a surface at body temperature. The shadow helps. It does not solve. And orbital geometry does not cooperate. Low Earth orbit means alternating between full sunlight and shadow every 45 minutes. The sunlit portion is not a passive event. Exterior suit surfaces in direct sunlight reach temperatures above 100 degrees, hot enough to boil water on contact. The side facing the sun and the side in shadow exist on the same object simultaneously, separated by the suit's own fabric. Engineers designing suits and spacecraft must account for a temperature swing of nearly 280 degrees across a single structure within a single orbit. The thermal challenge is not keeping warmth in during shadow. It is managing the simultaneous extremes across different surfaces, while the biological interior keeps producing its own independent heat source that neither sunlight nor shadow controls. The International Space Station solved this at scale. Its radiator panels, the large flat structures extending from the main truss that appear in every photograph of the station, exist for one purpose. They dump heat overboard. Their total surface area runs to approximately 2,500 square meters. That is half a football field of radiating surface, deployed specifically to dispose of the heat produced by the station's electronics, lighting, and crew. Not to heat the station, to cool it. Thermal management is one of the highest continuous engineering burdens on the station's systems. Every deep space mission proposal carries a heat rejection budget as a primary constraint alongside power and life support. The engineers do not write memos about heating requirements. They write memos about where the heat goes. A thermos does not generate heat. It only holds it. Your body in a vacuum is different. It is the heat source inside the thermos, and it will not stop producing. The vacuum does what a thermos does. It insulates nearly perfectly, blocks the fast exit channels, and leaves only the slow one. The slower the exit, the higher the internal temperature climbs. The higher it climbs, the less time remains before the biology fails. The physics of vacuum is not hostile in the way a cold environment is hostile. Cold attacks. Vacuum withholds. And withholding is worse, because withholding is invisible, and invisible threats do not trigger the responses that cold does. You do not feel a vacuum pulling heat from you. You feel warmth. You feel comfort for the first few minutes. Then the warmth stops feeling comfortable. By the time it feels wrong, 20 minutes have passed and the cooling system has been offline long enough that the options have already narrowed. The Nancy Grace Roman Space Telescope, currently in development, will characterize exoplanet atmospheres and planetary environments across hundreds of targets. The thermal design of the instrument is driven by the same engineering constraint that governs every spacecraft before it: heat rejection, not heat retention. Its detectors must be kept cold, which means the heat its electronics generate must be routed away with precision through radiators facing the correct sky orientation, away from solar input into the coldest available geometry of the background. Even the telescope designed to study other worlds is, at its operational core, a heat disposal problem. The Roman telescope will produce atmospheric data on dozens of potentially habitable planets. It will not tell anyone on those planets how to cool a suit when the sublimator stops working in orbit. That is an older problem, solved in engineering drawings and water separator schematics that most people have never seen, because the movies never showed them what the real threat looked like. The vacuum insulates. That is all it does, and that is enough.